Okay, good morning everybody. Today I am going to cover signal integrity mainly signal integrity for 1 hour and or so. Actually, this is the issues, this signal integrity issue in VLSI chip, mainly in digital chip, it's coming up mainly for the deep submicron technology. Earlier, it was not that much prominent. Okay, so one of the major issue of signal integrity is the crosstalk issue. So let's see what used to happen when we had technology library. Okay, by the way, you please try to be interactive. Okay, if you have any question, just stop me and ask me. Okay, above 0.25 micrometer technology or so. So this is, say this is your substrate. Okay, and say this wire, this is one wire segment, this is one wire, I mean this cross section of one wire, this is, so this wire is running into the page. Okay, these are also running, so these are all parallel nets going through like this. So definitely there will be a capacitance, signals are propagating through these wires, right? So there will be some capacitance from this wire to the substrate, which I am calling as CS, and from this wire to this wire there is a capacitance which I am calling as CW. Now earlier, for above 0.25 technology, micrometer technology, this CS used to dominate over CW. Okay, so the interaction between these two was not that much. Okay, because this was very less. So the STA engine is to model this CW as like this. The CS is there, here also CS will be there, and CW just take it in parallel to the substrate. Okay, so there is no interaction between these two. Okay, inside the capacitor what kind of current propagate? You have done electromagnetics, right? Yes. So we can understand from there itself, like if CW increases, why the interaction increases? Why? Just basic physics. This is one wire, this is another wire running. This is a capacitor. Okay, if there is a sudden change, what will happen to this voltage? So this is static. This is static. What will happen? Is the question is clear? Okay. You understood that the current through, I mean there are two kind of current, right? Conduction current, displacement current. So current through the capacitor is the displacement current, but that's not the point here. Okay, what I am trying to say is, if this is wire running, this is another parallel wire running, and there is a sudden voltage change here. Okay, how do you expect this fellow to behave? Depending on this capacitance value, of course it will depend, but say this is, I mean whatever you assume for this capacitance, how this is expected to behave. This is a static curve. This is a voltage, static voltage, 0 volt, say this is 0 volt, and so this is changing from 0 to 5 volt, right? The way it changes depends on the slope also. Okay, so say this is very stiff. Now how this guy will behave? Exponentially to so this will be charged, right? This node will be charged. This is not ground one, this is just another wire. Okay, so say this is also ground, I mean that doesn't matter. So there will be a little bit bump, right? Why? From the equation. Voltage across the capacitor, see from intuitive idea, the voltage across a capacitor, it doesn't allow to change abruptly, correct? So if this voltage change abruptly here, earlier how much was the voltage? Say this was 0 volt, this was 0 volt. So earlier the difference was 0 volt. Voltage across the capacitor was 0 volt. Now this guy changes to 5 volt. So this guy definitely will move towards 5 volt, correct? So that's the reason there will be a bump. Okay, this bump height may not be at 5 volt. Okay, it may not be that 5 volt. It might be some other value, maybe some intermediate value. Capacitor, if there is an abrupt change of voltage across a capacitor, the capacitor behaves like a short. Okay, so that's why if the driving strength of this fellow means the sleeve, this tan theta, okay, if it is very steep, this guy will try to dominate over this fellow. Say the driving, there is a driver, buffer is the driver. Okay, if this guy is dominating over this fellow, the current capability of this fellow is very strong compared to this fellow, so this guy will dominate over this fellow. Okay, this guy will also have some effect on this, but it can be negligible. Okay. Now, so what happens below 0.18 micrometer technology, CW is try to dominate over CS. Okay, because of the scaling effects. So the interaction between these two will be more. Okay, now one more point. If this capacitance increases, how do you prove that this interaction increases? If this capacitance increases, the interaction increases, means what? The effect of this fellow will be more towards this. How do you prove that? Pardon? Q is equal to C into V, right? Okay, dq by dt is C dV by dt. I assume C is constant. Then C is constant. C is changing from scaling down because of the scaling down. Earlier, CW was very, very less than CS. Now CW is comparable to CS. Okay, and greater than CS in fact. So if C increases, the I increases, correct? I means what? I is flowing through this fellow, so the interaction increases. Okay. So the timing analysis below 0.18 micrometer or so, I mean less than equal to 0.18 micrometer technology, it has to incorporate coupling capacitance effects between two wires. So there may be so many wires going through parallelly, maybe in this metal layer, some other metal layer, or maybe in the same metal layer. Okay, so all these effects the timing analysis engine has to take care. Otherwise, what might happen, there could be a timing failure, say setup or hold, or there could be a risk of functional failure also by due to the crosstalk induced noise. Okay, I shall show you how. So Synopsys provides along with its own static time analysis engine, which is called PT, prime time. There is a license, they take it completely license charge actually, which is called PTSI, prime time signal integrity. Okay, so that tool is actually capable of doing this crosstalk analysis. Even Astro also does have some kind of crosstalk analysis capability. It has to. You cannot go always back to the PT and do the crosstalk analysis. Astro means what? Placement routing, that tool. It can do a little bit of floor planning also. Okay, but not that much strong. Nowadays, they have come up with a tool which is called ICC, IC compiler. IC compiler actually hooked up the Jupyter XT. Jupyter XT is the Synopsys floor planner tool. So now you have IC compiler which can do a very good floor planning, placement, routing, but not yet Hercules stuff, that is the physical verification. So for physical verification, once again you have to go to the Hercules. Okay, So typically the flow with crosstalk analysis is first, so this is an intermediate closed design, this might be coming from the Astros, okay. That engine first you do the STA just without switching on the crosstalk analysis, okay. Once this is closed, this meets timing and all other aspects, then you switch on this crosstalk analysis fellow, okay. So what it does is, it doesn't calculate the whole delays and all, it calculates a delta delay effect due to the crosstalk effect, okay. That delta delay effect you incorporate, once again you run the equations, if you see that it's violating, you report it's violating, okay, otherwise you say it's not violating. So there are two things, crosstalk can induce either noise, which generally calls as static noise, or it can incorporate the delays also, okay. So the PTSI fellow, it has to do all these analysis, even glitch analysis also, because of this crosstalk, okay. So what is crosstalk? Once again, I mean, just this repetition. Crosstalk is the, I mean, this is the formal definition. Crosstalk is the transfer of a voltage transition from multiple switching nets, which are called aggressors, okay, to another static or switching net. The static net, which is called victim, okay, through a coupling capacitance between them, okay. Coupling capacitance means it's not actually physically existing, it has been coupled through the electrical phenomenon, okay. So this is aggressor, this is victim, this is also potential aggressor of this. But if this guy is strong, it's like, I mean, attraction between sun and moon within, I mean, earth is in between, right, it's same thing, okay. So the victim net could be static victim as well as switching victim. I mean, the victim could be a static voltage, say 0 volt or 5 volt, whatever, or it was during a switching, the transition was there, either 0 to 1 or 1 to 0. During that time, say B1 has more driving capability compared to B2. So what does it mean? This guy has steeper transition, this is stronger, this has steeper transition, that means this guy is faster actually, okay, generally. Now if this is stronger, so definitely say this was switching static, there was a voltage bump, or say it was moving like this green color, is it visible? This switching victim, if there was a moving like this, now because of this fellow it's moving up, right, it will move little bit up and then it will come down, right. So this is called switching victim, this is called static victim, depending on the, at that moment, what the net 2 belongs to, whether it is static or whether it is switching. Now every net inside your design is a potential aggressor to its neighboring nets and can affect multiple victims. That's okay, well understood, right? It's no problem. It can affect this fellow. It doesn't mean that its effects of left side gets changed. So from victim point of view, every net is a potential victim, even the aggressor. So aggressor and victim, this concept is a relative. If I try to calculate the crosstalk effect of this wire, that means if I try to calculate the crosstalk effect of this wire, all the neighboring nets, see, if a net belongs to here, after long gap, it's very intuitive that that cannot affect this fellow, right. So if all the neighboring nets are potential aggressor to it, these nets might be in the same layer or other nets, you do not know. If it is other layers, and if it is passing across, will it have much effect? Just think of it. So this net is moving like this horizontally, okay, and the other net is moving like this vertically. Will there be effect? Okay, if this wire is moving like this and this wire is moving like this, then definitely if there is a stiff transition, it will bump, right? if this wire is moving like this in one layer, say layer 1, and this wire is moving layer 2, will there be any effect? Why? But from here also it can affect this fellow, right? Chances decreases, right? Chances increases where? Where is the most chance? This node, right? So I'll show you, there is a concept called timing window. Say this guy is being driven by some other fellow, this guy is driven by some other fellow. If the time to this point and time to this point are same, crosstalk does affect, right? I mean, it's when it is reaching this point, when this is also reaching this point, there is a clash. It will affect, and then it will go. So, as I said, that every net is a victim net as or aggressor net. But you have to analyze in terms of victim. Assuming that this net is victim, what are the effects of the surrounding aggressors, potential aggressors? So a victim net can have multiple aggressors, definitely. So the crosstalk analysis must be iterative. It has to do this operation for all the victim nets, right? All possible victim nets. So you can understand the complexity of the problem in a millions of wire segments, in fact. Okay, you can understand the problem. As I said, the crosstalk can induce delay as well as noise. Okay, it's just for your, I mean, one slide short to understand. The crosstalk can induce delay as well as noise. If the noise is a problem, if the noise spike crosses the logic threshold of a downstream gate, otherwise noise doesn't make any difference. Say the voltage bump is propagating, if it crosses the logic threshold of it's going to an NAND gate, so AND gate, it is crosses the threshold voltage, then only it can make a switching on or off of a MOS gate, I mean MOS transistor, right? So otherwise it's not a problem. Yes. So actually, when you are saying the noise, I'll define the noise in the next slide itself. Okay, so that time I'll discuss this. Actually, yes, it depends on the not only width, it depends on the height also. I have not put in the slide. I'll discuss. So delay sometimes may make the victim faster also. It's not only make slower, it can make faster also. So if it makes faster, our effect is there could be a hold violation, there may not be a hold violation. If it is well within limit, it doesn't matter. There could be a possible hold violation, and may make slower means there could be a setup violation. Now let's see what is static noise. Static noise means this is stronger than this fellow, so this is transitioning like this, aggressor. Through this there is an interaction and there is a voltage bump, right? As you are pointing out, right here itself. So this is what? This is in time, and this is volt. Okay. Now say the voltage bump is a very short duration. Is it visible? Voltage bump is very short duration. Does it make any difference? Of sufficiently low height, say, I mean it's not very infinite height. Okay. Or say the voltage bump is very low height but sufficiently long duration. Does it make any difference? It also won't be able to make any difference, right? However, if the area is once again time, this is volt, so this is my voltage bump, intuitively this can make difference. Okay, actually it depends on this area. Okay, so the curve actually looks like this. This is, I am saying, height, which is in volt. This is I am calling as width of the bump. The curve actually looks like hyperbolic curve, something like this. So if you are well within this limit, there is no issue. Okay. Whereas if you are in this region, okay, in this region, it's a problem. Okay. This is called NIC, noise immunity curve. Okay. Of the bump. Just this is the height and width of the bump. This is called noise immunity curve. Okay. In fact, there is some terminology of noise margin, etc.
So this curve will be of the critical area.
Yes.
Less than that, you won't have any issues. More than that, you have.
Exactly. See, this height generally doesn't go after a certain time, right? I mean, it's a theoretical curve. But actually, say if you say that my curve is like this, okay. So if you are in this region, there is no issue. If you are in this region, there is a problem. Okay. This curve is actually supplied by the library vendor. This curve, the Crosstalk aware library, should have this characterization. Okay. Now, I give you one example of a functional failure due to static noise, where the static noise is happening in a clock path. The static noise can be in a data path or in some other path, anywhere. Okay. So here I am using the problem in the clock path. Say this is my aggressor, okay, and this is my victim. Victim is my clock. It doesn't mean that this has to be a clock. This could be a data signal also. So there was a small bump. So this is 0, this is VDD say, or this is some other level. This is VDD, okay, and I am assuming that this guy needs sufficiently bump, otherwise it cannot be etched, right, properly. So this is very low. It doesn't make any difference. If this buffer is not there, clock buffer is not there, it will simply propagate here. It won't make any difference. Clear? Now because of this buffer, this will amplify this fellow, right? So this is becoming stronger. So because of this, strength increases. Because of this buffer, this can act as an edge. So that extra edge will be coming here. So there will be a functional failure. Okay. Similarly, there could be a data. Say if this is coming in the data pin, so instead of 0, this could switch toggle to a 1. Okay. So all these things you need to take care when you are doing the crosstalk analysis. Now I am just giving showing pictorially that aggressor switching can affect victim switching in both ways. Say this is my aggressor switching. I am just for simplicity, I mean just for understanding purpose, I have taken 0 to 1. It could be 1 to 0. It doesn't matter. Now say this is my one victim. This is not there. Say this is not there. Okay. This is one victim. This is the aggressor of this victim. Okay. So this victim is also switching in the same direction, 0 to 1. If it is 1 to 0, this is also 1 to 0, something like that. So definitely this will make it to stronger. So this delta delay is actually shifting towards left. So that means victim became faster. Similarly, say this is my aggressor, this is my victim, and victim is switching in the opposite direction of the aggressor. So there is the curve will follow the red colored, right? See this black colored is what? Black colored is the weak transition due of the victim. See if you observe, this I have made little bit steeper compared to this. This I have gone 2 boxes, whereas here I have gone 2 boxes. here is only one boxes. You can see it's visible, this is stronger than this, right? So this will make a transition like this. So delta delay will be introduced. See where the transition, effective transition can happen, it's a 50% say. So from here to here it has switched, right? That's the delta delay you are calculating when you are doing the crosstalk analysis. So victim becomes slower here. Clear? Now you have done your power aware design, right? Professor Paul was taking. Actually, just remember one point. See, you have multiple buses running, 3 buses running. Okay, the signal can propagate from one to this direction. The signal can propagate from here to here direction, or here to here. Both directions possible. Sometimes, if you just route your signal path like this is propagating through this, and this is propagating through this, the coupling capacitance reduces. What I am saying, see, this bus is consuming some more power, lot of switching is there. Okay, and when you do the bus coding, when the bus capacitance is pretty high, basically say here is one peripheral, here is one peripheral at sufficiently long distance. So you are communicating through long buses. Long buses means what? Larger capacitance. It has to drive it. Correct. So then only you can go for the bus coding. If it is placed here itself, there is no point. Correct. Power is proportional to C V square F, and there is proportional to alpha C V square F. What is alpha? Yes, this is activity factor, right? Out of 1 millisecond, how long it's switching. So if this bus propagates like this, see, this is physically you are seeing here. Okay, this bus could be routed in a different way also. Or there may be some other peripheral here, right? These guys are also talking. This is TX, this is TX, this is RX, this is RX. And master slave. Okay, this is communicating towards this is also communicating. If you route this in parallelly, the coupling capacitance increases. If you route them differently, TX is this way, RX is this way, so the propagation is in this direction, opposite direction. Okay, so what you do is, this wire you make it here, this wire you make it here, this wire you make it here. The consecutive nets propagate in the opposite direction. Okay, so the coupling capacitance reduces, that means power reduces. This is one of the steps of power reduction. Now come back to our crosstalk stuff. The timing windows, okay, I just talked about. Always, if see, the interaction between the nets will be always there. Okay, now the problem is that whether that interaction will make any difference or not, that is we have to understand. Say this is synchronous design, there is another flop maybe somewhere here, right side, and this flip flop are driving through a mux. Okay, and see, interaction happens inside a net, right? See, I am pointing what happens to this point, just for understanding. Okay, so this is the shortest path and this is the longest path, okay, to propagate to this point. So through the shortest path, the signal can come early at this point, right? And through the longest path, the signal can propagate to this point maximum, after maximum time. We show this is the typical convention. We show this like this, that this window, it can reach out of anywhere in this window. Okay, this, now you take 50% of this earliest transition, 50% of this transition, you define a term called timing window. Okay, now look at this figure. this aggressor and this is my victim. Okay, this is the timing window of the aggressor, okay, and this is the timing window of the victim. Means what? The signals can propagate to that particular point up within this window or this window. So from your common sense, there is no overlap of time window, so no issue at all. Will there be any interaction? No. Right. Now, if aggressor and victim will have an overlapping in the timing window, so crosstalk delay need to be calculated. Correct. Now, I just make it one more little bit difficult. So the crosstalk effects will be here also. Right. So earlier, when you are calculating the shortest path and longest path, you are basically neglecting the crosstalk effect here. Now there could be a crosstalk effect here itself. So will that change this window, move left side, right side? So you understand the problem now, right? It's iterative problem. Now, okay, so far it's clear, right? I mean, it's very simple and straightforward. How CRPR I talked earlier yesterday. Clock convergence, pessimism removal. When you do that, when you are doing the on-chip variation analysis, okay? And today's world, you have to do it on-chip variation, okay? So, how CRPR should be treated in SI analysis? SI means single entity analysis, okay? So, just remember this figure. There is a clock, there is a buffer. This is my data path. This is my clock path. So, for setup, you will be calculating the max here, and for clock path, you will be calculating minimum, and for hold, it will be ulta, right? Now that clock was in common, that was common buffer, so there was no point of calculating in both max. So you remove the pessimism, which is called CRP, right? So that CRP was defined by max of this delay of minus min of this delay, this buffer delay, right? Now from your common sense, can you tell me how this CRPR has to be? So you didn't feel, I was expecting that question that time, sir, if it is very simple, you have to minus this, and this is in common path, why don't you calculate the timing from here itself? I was expecting this question actually. I mean, why the synopsis fellow is so stupid that they have incorporated one concept called CRPR? Is it for interview purpose? Right? It got my question. I mean, if you are not aware of SI, you can't answer this. Actually, during SI, we need to take care of CRPR in a different way. So, what do you think? Just from here, should I remove this CRP? When I am doing the, see, this CRP was removed during setup as well as hold analysis earlier when I was doing the STA analysis without SI effects. Now I am incorporating the SI effects. So whether I should remove the CRP or not, that is my question. Can you answer me from your common sense? Definitely the answer is no. Otherwise, why I am asking? But now you tell me that whether I should remove it for setup or hold both, or I mean, should not remove for setup and hold both. Then I will understand you understood setup and hold. Anything, any point you can think of? See, I have just shown these nets. Assume there are so many nets running parallelly.
So even at that point, the crosstalk happens before this.
Before this buffer?
Before reaching the point at which you are saying.
This point or this point? This point.
Yes,
Okay.
and you cannot say that we can take the timing from here for all the signals.
if crosstalk affects here,
before this only means at this point we are saying we can take from here because
okay, so crosstalk affects equally for this buffer.
yes,
Yes, then
at this point we can never say that we can leave out this buffer.
CRP.
Yes,
You can remove CRP.
because
Yes, yes. Any guess for setup analysis? Okay, the windows, the moment I am getting affected, whether I will be affected after 1 second, same way. It's not guaranteed, right? For setup analysis, which edges you take? Is it the same edge? A different edge. So for setup analysis, the edges are coming in different time, right? So the moment it will affect this edge, launching edge and capturing edge are different. So the way they might be affected are also different. Okay. So just for example, this is the buffers. Okay. This is the aggressor, coupling capacitance. This is my aggressor, transition is happening. This is clock, whatever, habi jabi. This I've just taken one example, and this area is basically the window. This blue colored stuff. This is the window. Okay. Now it may happen. This is my clock, right? So this is the window of this clock transition. Here, correct. Now see, the window is overlapping here. The window may not overlap at all, or even if there is an overlap, right, the way this guy is transitioning, say this is a 1 to 0 transition, this is 0 to 1 transition, it could be different. The sleeve might be different. Sleeve means the flatness, right? So even if there is an overlap, the effect might be different. So say for example, this guy has become slower, that has no effect. Here is no effect because the window doesn't overlap at all. This is one example. This could be some other effect. Okay. So when you are doing the setup analysis with SI switching on, you have to have CRP on. I mean, you cannot remove it. Clear? This is definitely your interview question. I'm really honest. I'm saying you, this is your interview question. What they can ask other than this? Okay, this is what I have written. But for hold analysis, we are analyzing with the same edge. The first guy, the launching pad, the launching flock is affected by the second edge, and that is getting affected. And here also I am taking the data, capturing the data with the same edge, right? I told you the effect. I mean, hold analysis generally we do it with the same edge, and setup analysis with the different edge. So that's why for hold analysis you can still remove the CRP. But if you don't remove, doesn't matter. It doesn't matter as long as it is passing. If it is not passing and you want to push the performance, you have to remove the CRP and see whether it is really failure or not. Clear? Now, I have not. Now the question is, if there is a multi-cycle path, whether this is always true. Just remember, when you are talking about multi-cycle path, depending on your different scenario, the way you have designed, okay, the edges of setup analysis could be different also. See, multi-cycle path means what? Your clock is like this moving, right? So this is a capture clock. It may not be in same frequency, okay, always. This and this, say you are doing the setup analysis. It may happen you are doing the hold analysis with respect to this edge. It may happen. In my example, yesterday's example, I had shown you this and this edge was the hold analysis. It may happen is these two are hold analysis. So you should not remove the CRP. So the concept of CRP or removal of CRP is, the fundamental point is, if it affects in the same edge at that time, same time, you can remove it. Otherwise, you cannot remove it. Okay. So static this signal integrity issues I thought I'll cover this much only. So now time is there, so I start with little bit of backend flow. Okay, just the small see, this is called, so this box I'm calling as core. Core in the sense I will be placing now. I mean those are the concepts. Okay, so static time analysis and the signal integrity. Actually, there are also a lot of methodologies are there. I have not covered methodologies because first you have to have concept, then only you can go for methodology. Methodology means it's a recommended steps either by your own company people, experienced people, or maybe it's a joint activity with Synopsys or some other vendor. Okay, so methodology is basically the steps which you need to follow. Okay, so this is the core. Core means my standard cell I will place here. Okay. Okay. By the way, what is standard in a standard cell? I am telling that, say this is one standard cell. So it has width, it has height. Correct? See, I'm not drawing the in between those connections and all. When I'm doing the placing of a, so I'm trying to place this fellow. What I need is this coordinate, right? XY coordinate, nothing else. The shape of this. So standard cells are defined by height and width. So what is standard in a standard cell? I'm talking about say 0.18 micron. It is the height what remains same. The width can be varied. So the next cell could be of same height but different width. Is it clear? This is one standard cell 1, this is C2. Okay. So all these cells I have to place cells as well as macros. Okay. Macros means say FFT, one particular company is giving you that FFT block. Okay. That you are directly hooking up. So macros you have to have handcrafting placement. You place it here, say. Okay. This is one macro. So this remaining place you can place these standard cells. Okay. This is called core. Out of this core, there would be a power ring. It's so in the lab. 2 rings will be there. Okay. One ring corresponds to VDD. Other ring correspond to VSS. Okay. So whenever I am drawing it like this is my core. When I am drawing it like this, basically left side is routed through one particular metal layer. This and this could be in different metal layer, or this and this also could be in different metal layers. It depends on you and your experience. Okay, what to be done. Now, after this, there is a something area which are called pad area. Is it visible? So I will be connecting I will be placing my pads here, left side, right side, all sides. Okay. So all the signals which has to be coming here, okay, inside this core has to be connected through a pad. Pad means it's a metal with some other circuitry. What are those? ESD circuitry, electrostatic discharge and all the stuff. Now there is a cavity after this. I am not drawing the right side, it's actually the same way it's coming. Okay, it's same all around. This is called cavity. And then your pin will be there, pin inductance. Okay, so this is my package. The leftmost boundary is my package. So the pin to the pad, there is a connection which is called bond wire. Okay. So this is the overall looks of any chip.
Why pads are required?
Why pads are required?
For ESD.
Okay, if there is no ESD, why pads are required? How can you connect to this fellow? This is a metal, right? You have to give the external signal to a metal. The intermediate connections, how can you connect it through this? There are wires only. These are all wires moving here. Some internal connections are moving here. This is the wire. That is of very thin length, right? And how can you connect it through this? So there will be a bond wire. Exact physics and all I am also not aware. I'm not sure. And why in between there is a wire particularly called bond wire. I studied long back. There is some polysilicon wire. It's wire technology itself is pretty huge. These connections. So for example, this routing, whether you will be doing 90-degree angle or 45-degree angle, that also matters. There are so many electromagnetic effects. Antenna effects are there. Electromagnetic. So for example, if you are connecting like this 45-degree angle or you are moving this 90-degree angle, this is a potential antenna. But definitely the signals are moving and then it's bending, right? So in your lab today, you will be actually doing this core placement only. Okay, because our NASA semiconductor pads we are not able to handle today. There is no flow is ready in our lab. Okay, generally it should come from the experienced people who had already done it. There is no actually what happens on these tool sets, it keeps on changing. So I was able to connect these pads, but unfortunately it was giving some error. I do not know why. I didn't dig out those things. So this is your core. What you do is during placement, okay, first of all you have to have a floor planning for this. See, floor planning means all this planning. See, this is core, here to here gap, here to here gap, here to here gap, which metal layer it will be, which metal layer it should be, all those planning, okay, plus some other planning. How many rows you should have? So this is one row, this is another row, this is another row. I will place the standard cells only around these rows. The height of these rows are same. This is for ASIC. I am not sure about FPGA. Okay. Then, so definitely there could be something called core utilization ratio and some concept, the theoretical concept. If there are more number of rows, definitely you are utilizing it much better way. But routing congestion may be affected. Now, say this is one cell you have placed, standard cells, okay, and VDD line is moving here. This is my VDD line, say. So from here to here, the distance is pretty huge. VDD is, so you draw it properly, putting it red line. So VDD is, so from here to here, it's a huge IR drop can happen. So this is my 1.8 volt. And here say maybe the voltage is reaching which is 1.5 volt, but I had told you it has to be greater than 1.6 volt, greater than or equal to, so it's not allowed. So what you have to do from common sense, I should have some kind of power straps. These are called straps, these are called rings, okay. So I draw this like this is another metal layer. The powers are moving like this. So for this fellow, the power it will take it from here itself. It's very small distance, right? So these are called power straps and power mesh. This is called power ring. Okay. Similarly, there should be some ground ring also. So when it will be here, there should be some ground pin also, right? And the ground is something like this, ground strap. Okay. This power strap also you can make like this as well as horizontal. Generally we follow only one direction. Okay. Once these things are done, okay. So basically now you assume that your floor plan is ready to be placed. Okay. Once these are all done, what you do is you take your net list. Okay. During floor planning also you should have the, you have to have the netlist in your hand because all these things you are doing with your netlist only. The area it has to take. For example, this core area, either you have a already existing footprint because you are working in a company and they have a market, or say for your case maybe it has to be defined by yourself, right? This W and this. In the script probably you have seen I have defined it's called 200 200, the width and this. So this one you can do it automatic also. You can say that I define one term called aspect ratio, which is H by W or something. H means this one by W of the core. So I define it by 0.7 or say 1. So it will be always a square type set, but it will take automatically. Then you will say that it's not meeting the area, it's not able to route, place it or everything. It's that the area of this core area is very narrow compared to your whole netlist area. So what I prefer is, by your intelligence, you prefer to give this estimated area. Okay, that's what I have done in my this thing script. So
one thing other than path is if you have a layer for path, for ground we have a layer.
yes,
Then it can reduce the interference. Other than strips, if you have a layer dedicated to power, one layer dedicated to.
what is the point? If one layer dedicated means if you have one layer here, how can you route the other layers?
That will be, that bias will be there in that case, no ground.
No, that's what it is there, right? These things are generally done in one single layer. So this is done in metal 1, and these things are done in say metal 3.
Means whole layer is totally ground or whole layer is power.
It depends. It depends. His question is whether I will have a dedicated layer, say metal 1 layers. Metal 1 means the first edge, first layer. Metal 1 layers for ground. All the wires going to ground, but that's a poor utilization.
So layers if you increase
No, wait. You say I define only 3 wires to be in your stack. Okay, and I have how many vertical lines I can have in a metal wire? Say 100. Now it is up to you that whether these are my ground lines, right? Ground steps. Whether I am using only 3 and I won't allow anybody to use other layers. Now his question is that if you do not allow, you are in safe side. What you are doing? You are reducing the effect of interference. There is a term called ground bounds, all the stuff is there, power bounds. Okay, now my question is, to reduce the interference, you can do that. Okay, if this is my strap, you do not use some neighborhood of that strap, and rest you can use. What's the point there? And that will also do the same thing, right? So it depends on your experience. Depends on, so you have a small chip and you have 6 layers. You can dedicatedly give one metal 1 and you can sleep, no problem. So all these things comes from experience and lots of experiment. I mean, so the backend engineer has to do it on loop. They will be in loop. You will see in your company the backend engineers staying overnight. They are doing nothing actually, only these experiments. Okay, trying to find out the optimized this one and this one, number of steps, all those stuff. Okay. Okay, where I were? Okay. When you have fixed your floor plan, you take the netlist. First, what you do is remove the clock buffers. Clock buffer, reset buffer, etc. Okay. I mean, you keeping the functionality same, just make it very clean. Why? Because the synthesis tool did not have the placement knowledge, right? So it worked in a different way. Now you have that luxury to have the exact estimated placement, right? You'll be doing some rough placement and all. So when you do this, after that you go for a rough placement. Okay, this placement, and then you connect all the power and ground pins, PG pins of the cells. Okay, it's actually very big methodology. I mean, you can from your script itself you can see that that's nothing actually. The methodology is, I can say, at least 50 pages. Okay, you have to have scanned, if there is a scan, what to do, if there is a clock tree synthesis, how do you do. Inside clock tree synthesis, there was a say it can be a 3 days training. Clock tree synthesis is never ending, because it depends on your actual design scenario. So typical this scenario is there, what do you do? This scenario is there, what do you do? All these things has to be there in the methodology. So typically you do that power ground connections. Power ground connections means those are the, see, generally in your standard cell, no, this is your standard cell. This side will be VDD, okay, rail. That standard cell will also have some metal rail, right, characterized in your library, and this is your ground, right. So what they do is these straps will run and they will just overlap on this. This is VDD strap, this is ground strap. So those are connected, correct. Now after doing all these connections and all, then you can go for, I think, clock tree synthesis. Okay. Once clock tree synthesis means what? It's balancing the skews. Balancing the skews between different clock nets. I mean clock points where it is reaching, the flip-flop etching point. Okay. So once that is done, you go for routing. Actually, every time you do for placement or routing, what you have to look for is the congestion map. Okay. Apart from that, there is the airdrop map. Okay. Congestion map means what? Congestion map means, say, okay, after this you have to go for routing. Every time, what you have to do is, say, this is my chip. If I do a virtual placement like this, okay, I have to have these many horizontal connections, n number of horizontal connections. I should have. If I place it this way, I should have n number of horizontal connections. Now I have only m number of connections. This is my demand. This is my supply. You cannot increase this, right? So as long as n is greater than m, it's called congested. So you have to change your placement once again. This congestion removal is pretty huge. For our chip, I had seen the congestion removal of Viterbi sequentiator. It took 2 months time just to remove the congestion and fit in the existing footprint. If you relax the footprint, increase the chip, then the other company who is buying your chip, he won't buy it, but you can sleep well, right? But otherwise, this congestion, I mean, you can understand if there is a loop, particularly say there is a loop, you cannot place those loops in far away, right? So you have to do that also in mind. Now,
is it done with a tool or it's done by human or something?
it's mostly done by tool, but you have to guide the tool every moment. The tool doesn't have that much knowledge, correct? What you do is basically, you can do a timing aware physical synthesis, you can do a area aware physical synthesis. Timing aware means you should have that SDF, SPAF, the timing information with yourself, right? Then it will try to place those cells which are in tightly critical path closer. If you place them closer, okay, if you place them closer, the routability congestion is increases. You have to far away, right? Once if you are moving it far away, the problem becomes it's not meeting the timing. It's an iterative process. The backend engineer really dig into these things. So once this congestion happens, all these things are met, just go for routing finally, and then just placement. After placement, you just go for routing. Routing is nothing, I mean just connections of these layers, and then there is a stream file. See, you cannot send your layout to one vendor. Say you are using one, say TI, this FabLab, right? The FabLab guys does not have this design information. They will accept in one particular format, which is called GDS2. So there is a stream file. With that stream file, you have to convert your layout information to the GDS2, and that GDS2 they will take and work on this. If the physical verification is clean, a lot of checks are there. DRC checks are there. Physical DRC is different from logical DRC. Logical DRC, what I said, max tran, max trans means transition, max fan out, and max cap. Here the physical DRC is something different. Say just physical DRC क्या होता है? Say this is one metal, right? This metal width is this, right? The the metal width should be minimum of one particular, say 1 nanometer. This is one DRC. The metal wires, gap between two metal wires, center point has to be of, say minimum is of d mean. This is one constraint. You cannot, you can define on your own constraint also. Metal wire, metal one, you cannot go through, you cannot connect ground. This could be your DRC. That is written in your text file. That 5lm.tf file yesterday you had seen. Open that, you see that. Okay, those DRCs will be written. There are so many rules in that. There are antenna rules. Thousands of rules will be written there. All those things has to be met. Then only those checks. See, when you are doing the physical verification with Astro, okay, what you are making sure is the rough DRC, a rough kind of physical verification. Why you have to go for Hercules? Astro does work on this view only, this boundary only, because it does the placement only. It's a placement engine and routing engine. It does require what? The coordinate and where the connection has to be. Correct? This information is sufficient. When you go for Hercules, what it does is, it goes inside of this cell. Okay, there is a connection like this, there is a connection like this. Now it try to calculate all the effects, okay, and try to clean up your physical verification process. So all these things you have to do, and then only you can say do a tape out. Thank you. Thank you. This is too much. Backend actually is too much. I mean,